Hello, everyone. Come on in. Oh, I'm letting you in even early. Ooh, fancy. 2 whole minutes. Think. Let's check what Steve Jobs says. Nope, right on time, according to Steve Jobs, who, of course, passed away, but still, the main thing is, I suspect his timepiece has a correct time on it. I hope everybody had a great weekend. Does anyone have any questions for me? I did make some changes to all the dates on the homeworks. Make sure you check those out and get those done on time. I think I might have actually had to pull a chapter homework and make it due earlier than it was, because it was like clearly a typo or something. You got a practice test as well and a test that's coming up, so make sure y'all check on those deadlines. But other than that, I guess we got 7 people here. I guess we should go ahead and go. No one has any questions? Oh, another person came in. Woo! All right. So last time we talked, since it seems we don't have another person came in. Since it doesn't seem we have any questions, I want to remind you guys to make sure you check your homework list on my lab and mastering for all those due dates. Remember, I allow you to turn in late, but you're going to get points taken off, and I really don't want to take points off, because that's sort of a lifeline, because as you can tell, midterms and finals tend to not get that great of scores. Those are the ones that are graded in a sort of face-to-face fashion. Maybe 50% of the class does okay on them, but the other 50% not so well. So those are your only lifeboat guys. So make sure y'all try to learn the material well, and of course have a buffer ready just in case you screw something up. So make sure you check, as I said, mastering, my lab and mastering for your homework, so that are due, what their due dates are. Put them in your phone if you have to with an alarm. Check in Canvas and look for when tests are due. Usually I set the practice test due on the same date that the actual test is due, just because what's the purpose in taking a practice test for test 5 after the test 5 is done? It's not much, in fact, but I've discovered that students tend to do that at the end of the semester when they realize, oh, my grades get terrible, I didn't take enough practice tests. Well, you sort of defeated the purpose, so you're not going to get to now. So that's why I take them down. Anyone, last chance, have any questions before we get started?
Is the practice test supposed to be up right now?
Yes, there was supposed to be one up right now. Let me double check.
Yeah.
Thank you for asking that.
And I don't see
it. Okay. Oh, there I am. Nope, that's not where I am. There I am. Oh, I hit the wrong button. That was not helpful. Not helpful at all. Okay. All right. So what do I have up? I am in my modules for this course. And what I see, and I might be misremembering tests, I mean a class, if I told you guys that some particular module or that some particular practice test is open. So right now I have a practice test that covers chapters 29, 30, and 31. Have you guys done, and that test was already due, or excuse me, yes, that test was already due. So it looks like I did not have one open yet. I see I made it, but I did not make it available to you. Let me go ahead and put that practice test up now. This is chapter 17, 18, 19, and then again, it's also got a little bit of 20. Thank you for asking me that. That was a perfect question at the perfect time. The practice test should now be up. Well, I'm putting it up as we speak. So what I'm doing is I'm making its due date. We meet on Mondays, so I'm gonna make its due date 4/17 at 11:59 p.m. Actually, let me give you that Tuesday. So 4/19 at 11:59 p.m. is the due date for the practice test, which means that's going to be the same date that the test is due. So make sure you guys get that done in time. So this is April, right? Yeah. Okay, so yes, now we have practice test 6, which covers 17, 18, 19, and 20. Has been posted. Thanks for checking on that. That one actually I had made and had it all set up and everything was ready to roll. I just forgot to launch it. So thank you for that. The test will probably be up. I'm thinking maybe Thursday, because what's going to happen is I will finish up chapter 19 tonight. Chapter 20 I will do next time. Since I gave you until the Tuesday to get tests done, that gives you a day to ask me a question Monday if you have any. I'm not going really deep in chapter 20. I just need you to know your book gives you several, and I mean several versions of the second law of thermodynamics, and I want you to know all of them. Okay. I'm not gonna make you solve a buttload of problems. I mean, there's a homework set with it and stuff, but as far as the actual test goes, I'm not gonna make you solve a buttload of problems from chapter 20. Even though you'll get plenty of practice for your homework and your practice test. I want to just make sure you definitely know the second law of thermodynamics and its various forms. And actually, that's sort of the cool thing. All those different forms have been proven to be equivalent. So we're now at 11 students in the class. So that makes me feel a little better than starting with 7 students in the class. Last time I gave you that diagram of basically what would happen if you took a kilogram of ice at negative 40 degrees Celsius. And I just dropped a pin. So I said, what would happen if you took a kilogram of ice at negative 40 degrees Celsius and you slowly raised it up until it was basically steam at, say, 120 degrees Celsius. So what we saw was a graph where basically for some period of time, the temperature climbed until it got to 0 degrees Celsius, at which case the temperature stopped changing. But I kept having to add heat. And in fact, that horizontal graph was kilocalories. And by the time I'd gotten to 20 kilocalories, I had brought the ice from negative 40 to 0. And then I went another 80. It's actually 79.7 kilocalories is what had to be added to actually convert all of that solid ice into liquid water. That's called the latent heat of fusion. Okay. Students sometimes have a hard time remembering whether that's heat being absorbed or heat given off or that sort of thing. So that's why instead of me using calorimetry as delta Q equals 0, I put everything that's losing heat and everything, in other words, like everything that's cooling down, I add all those terms together, and then I set that equal to everything that's gaining heat, i.e. everything that's warming up. That way, everything just has to be positive. And of course, you have to break the rule that delta T is always final minus initial. Other than that, that's the pretty much the only time you have to break the rule that delta means final minus initial. Okay, so after that, after we added that extra 79.7 kilocalories to that 1 kilogram of solid ice, all of the solid ice had in fact now become water. And then the temperature rose and rose and rose from 0 degrees Celsius, all the way up to 100 degrees Celsius. And then the temperature locked down again and was fixed at 100 degrees Celsius. And it stayed there and stayed there and stayed, and it stayed there. In fact, at that point, it was, I think, 200 calories had been put in, kilocalories had been put in. And in fact, it stayed there until I got all the way up to 740 kilocalories. In other words, it took 540 kilocalories for that 1 kilogram of liquid water to transform, i.e. break the pseudo bonds that it had as a liquid so that it could become a gas. That is the latent heat of vaporization. Okay, again, remembering whether that's a positive or negative heat is a little bit difficult. So just always think what's losing heat, what's gaining heat, set them equal to each other. That's calorimetry. once I got through that 550 kilocalories for 1 kilogram of liquid water to turn into steam, then it sloped back up again. And as I added more and more kilocalories, the temperature of the steam just got larger and larger and larger. And what we saw, in fact, was that if you take the reciprocal of those slopes, you'd actually get the specific heat. For instance, the slope of the ice one going from -40 to -40 to 0, the slope was like 2. If you flip that over, that's about 0.5. And if I remember correctly, the specific heat of ice is 0.55 kilocalories per kilogram, or calories per gram per degree Celsius. Okay. Similarly, water actually has a specific heat of 1 kilocalorie per kilogram per Celsius degree. But as you'll see also, water in the steam form has a different specific heat as well. So keep that in mind whenever you're solving problems. You've got to realize there's a difference. Okay. So that was the last thing we covered, and really that gave us another formula. So we already had, let me write down the formula we had, and I'll write down the new formula we have. So the formula we had was that Q is equal to MC delta T. Again, that delta T normally means final minus initial. And if you want to know whether it's a positive amount of heat or negative amount of heat, then you better use final minus initial. But like I said, when we're doing calorimetry experiments or calorimetry calculations, you're going to ignore that rule. Now, the new formula is, it turns out that if you want to change the state, you have to add an amount of heat Q or take out an amount of heat Q. And that's given by M times L, where L is the heat of, and there's a bunch of different words. There's heat of fusion, and that's really the heat in going from, say, a liquid to a solid. There's heat of vaporization, which is going, in fact, from a liquid to a gas. And what about dry ice? Does anybody know what we would call that?
Sublimation.
There you go, heat of sublimation. So there's actually that kind too. And in fact, dry ice isn't the only one. It's just dry ice is the only one that does it in the normal everyday temperature realms that we deal with. So some other things do it as well. For instance, if you put a pot of water on the surface of Mars, it doesn't have a high enough pressure to maintain in the liquid state. And in fact, it'll immediately boil away just from the lack of pressure. So even though it's way, way colder than freezing. So that's some of the weird things that other materials do. So that's just a new term. We just have to remember, multiply M times the heat of fusion or heat of vaporization or whatever it is, and remember which one we're doing. Now, to give you some idea about this, those of you who live in the maybe Virginia Beach area probably heard about the Strawberry Festival and all that stuff. And you probably also heard, like, when we have our first frost, you'll hear the weatherman talking about the strawberry growers spraying their strawberries. That's a very common practice, because what's going on there is, if you see that the night air is going to reach 32 degrees Celsius, or excuse me, 32 degrees Fahrenheit, or 0 degrees Celsius, or even lower, and you go ahead and spray water all over your strawberries, you might think, well, that's terrible, you're going to freeze them. But in some sense, that is what you're going to do. But when you actually spray those strawberries, what happens is that strawberry, if it's wet, when it reaches freezing, it will actually freeze. And to go from a liquid state to a solid state, you actually have to give up energy. That's one of those times where you can know whether this is a positive or negative. It actually has to give up energy to go from a liquid state to a solid state. So not only does the little strawberries get a nice little ice jacket to keep them a little warmer, but they get a little heater in the pocket too, because the instant it transforms from from liquid to solid, it actually gives it a little boost of temperature. So it's a little bit warmer than freezing. So if that ever helps you as far as keeping your signs straight about heat of vaporization, heat of sublimation, heat of fusion, that kind of stuff, then yay, we've accomplished something. All right, so last time we had also worked a problem about tea, and I talked about the perfect iced tea is tea that's at 0 degrees Celsius. So let's imagine now having let's say we have 8 liters of tea at 90.0 degrees Celsius. Okay. So I have 8 liters of tea. Now that's super strong tea. That's tea that we've just boiled with. We're going to make so much tea that we actually boiled it, say, with 22 bags of tea. So it's super strong. We definitely want to water that tea down. But we ideally like to make iced tea. And we decide to add, let's say, 2.50 kilograms of ice at, let's say, negative 20.0 degrees Celsius to the tea, which again is just water. Is this enough? Whoa, I don't know what word I was getting right here. Oh, check this out. I forget I got a eraser. Wow, fancy. Is this enough ice to bring all of the tea mixture to 0.00 degrees Celsius? So there's our big question. Okay, so what I'm going to do with this is I'm going to start off by just saying, well, let's see exactly how much heat do I have to remove from 8 liters of tea at 90 degrees Celsius to bring it down to 0 degrees Celsius. So that's the way I'm going to try to solve it. I think red shows up pretty good here. I've decided that green really looks like crap, so I'm going to try like this. So first, how much heat must be removed from the hot tea? Of course, Christopher Hitchens would say that tea, of course, Christopher Hitchens is no longer living, but still Christopher Hitchens would say that hot tea is not nearly hot enough. It should be at a piping 100 degrees Celsius, or it's just not a good a British tea. So anyways, let's check it out. So it turns out that Q equals MC delta T. Assuming again that we have water, which is what tea is. Remember, tea is just basically water with tainted, if you will, with tea. So 8 liters of water, remember, the density of water is equal to 1 kilogram per liter. And that's the one that's most relevant here. So we're going to say that's 8 kilograms or 8,000 grams. And I'll put a decimal there because that shows me that I have all 4 sig figs, which really I should put a decimal somewhere else, but I really should only have 3 sig figs, as you can tell there, but no big deal. And I put it in grams specifically because I like using the calorie version in thermodynamics, because the calorie version of the specific heat of water is really, really hard to remember. It's 1.00 calories per gram Celsius degree. And in this case, I just want to know the total value. So I want to do big number minus small number instead of worrying about final minus initial. If I did do final minus initial, obviously the final temperature would be 0 and the initial temperature would be 90, and you'd see that it actually has to lose heat. And that's what I said. I said removed it. So that's sufficient too. So if you want to know how much heat must be removed, I'm going to give it to you in a positive answer. And that positive answer is 90.0 degrees Celsius minus 0.00 degrees Celsius. And let's calculate that. And let's pretend that my glasses are going to work good enough. So I'm going to say 8,000 times 1. Oh, I got that one. I can do that in my head. Times parentheses 90 minus 0. I can do that in my head too. Ooh, man, I am on fire today. And that would be 720,000 calories. And I should have 3 sig figs. So I'm going to say 720 times 10 to the third calories. And that's a lowercase c. I shouldn't have written it so big like that. So 720,000 calories. Now let's see how much heat must be added to bring the ice, first off, from negative 20 degrees Celsius to 0 degrees Celsius. So how much heat is required to bring, and we said 2.50 kilograms of ice from negative 20.0 degrees Celsius to 0.00 degrees Celsius. Okay, well, if I look in my table in your book, which I think was on page 499, let's check. It was table 19.1, if I remember correctly. Yes, it was table 19.1. And the specific heat of water in calories per gram or in kilocalories per kilogram. And this is roughly at -5, so I'm going to assume that's close enough. But that is 0.50. So that's 0.50. So Q for this part is 2.5 or 2,500 grams times 0.50 calories per gram Celsius degree times, now again, I'm just going to try to do big numbers minus small number because I just want to get a quantity of heat, specifically a positive quantity. So I'm going to say my big number is 0 and my small number is minus negative 20.0 degrees Celsius. When I do that, I go 2,500 times 0.5 times, obviously this is just plain 20, and that gives me 25,000 times 10 to the third calories. So that's definitely not going to do it. We need 720,000 calories. I've only gotten up to 25 calories just by bringing the water up to 0 degrees Celsius. But I still got, remember, I've got the heat of fusion, or the heat of fusion that's required to break the lattice, the pseudo lattice, if you will, of the water up in ice form. So how much heat is required to change. We've already got all of it up to 0 degrees Celsius to change 2.50 kilograms of H2O from from solid at 0.00 degrees Celsius to a liquid at 0.00 degrees Celsius. Okay, well, that equation is just Q is equal to M times L, and that we also have a table for, and that table is in fact, I think on page 507, maybe. Let's see. Definitely not there, definitely not there, not 507, not 504. Nope, it was on 503. There you go. And it says, in fact, the heat of fusion for water, oh, and I even stated it earlier, I don't know why I didn't remember it, 79.7 calories per gram. So I'm going to say 79.7 calories per gram times, notice I put the order backwards, that's because I'm a moron. And then this would be times 2,500 grams. So what I'm going to do is up. So what I'm going to do is I'm going to take 79.7 and I'm going to multiply that by 2,500, and this is giving me some hope that we might actually pull it off this time. In fact, this time we get 199,250. Whoa. 199,000 times, and notice that's 250, so that doesn't round up, times 10 to the third calories. So no, that's still not enough. We've now got 200 plus 25. We got 225 total calories. So 2.5 kilograms of ice is insufficient to turn 8 kilograms of tart tea to iced tea. We needed 720 kcals, but could only steal 225 kcals. Bummer, huh? Any questions on that? Now, we could have tried and said, maybe we want to mix it half and half, 8 kilograms to 8 kilograms. That would probably make, well, hell, even if I just doubled it, that'd make it 5. And if I tripled it, that'd make it 7.5. So that's pretty close. So that would make 600 plus 3 times 25. So 675. Even that would, well, yeah, even that wouldn't do it. So we need more than triple this amount of ice to bring it up there. You guys can give that a try if you'd like. I'll count it as an extra credit problem if anybody wants to work out how much ice would have to be added to turn that 8 kilograms at 90 degrees Celsius into 1 iced tea, but 2, tell me what percent is water and what percent is tea, and tell me how many total kilograms of it's left. So that's a neat little extra credit problem you can try if you want. So I'll just write here extra credit. How much ice at negative 20.0 degrees Celsius would it take? And I don't know why I wrote that as an M, but and what mass would be the tart tea and what mass would be pure H2O, and I'll say IE percent would be fine. Okay, so that's an extra credit, and like I do all my extra credits, they count as a another homework assignment that I'll drop as your lowest grade. So if anybody wants to give that a try. Anybody have any questions on any of that so far? I was pretty confident I had a pen out, but it appears I have a screwdriver out instead. So that was not what was intended. Oh, here's his pen. Okay, I found it. Okay. Yeah, it's not good, Makita. I'm glad somebody thought that was funny. Anybody have any questions about how that was done? That makes sense, right? That should be pretty straightforward types of physics problem. Okay, so what we're going to do now is I'm going to stop and talk about something a little bit bigger deal. So in other words, we're going to go from some of these more mundane problems, which, you know, these problems are pretty straightforward. They're straight out of a typical chemistry class, but there's some other things we can use. And I'm not even going to waste time doing the derivations. I think my derivations are online anyways, if you wanted to, but I'm going to talk about the first law of thermodynamics. And then I'm going to talk about the different processes that can happen in thermodynamics. And then finally, I'm going to give you some equations that we can use for, I shouldn't say finally, that we can use regarding specific heat in a very specific way. And then finally, I will tell you how heat is transferred. So, and that's pretty much all we have left for this chapter. So first off, I want to tell you what the first law of thermodynamics is. So here's the first law of thermodynamics. First law of thermodynamics says that you have an internal energy, okay, and we're going to call that E internal. Some books will use U or something like that. And what that internal energy is that internal energy is not only all the kinetic energy of the atoms and the molecules making up the sample that you're looking at in terms of them moving left, right, in, out, or up, down. It's all that plus all their other degrees of freedom. So in other words, when you add heat to a substance or a sample or something you're wishing to study, some of that heat's going to go into making the atoms move left and right. Some's going to make it go into making it go in and out of the page, and then some's going to make it go up and down. Okay, so there's your X, there's your Y, there's your Z, and that's just the center of masses of the atoms and molecules. But you're also going to have molecules that look like dumbbells, in which case that molecule that looks like a dumbbell could spin about this axis, but it could also spin about this axis. Okay. Turns out also it can be caused by kinetic energy that these two atoms have by vibrating back and forth. And it turns out they can also have a 1/2 kx squared energy just because it's compressing like a spring. And that's just diatomic. We haven't even gotten to, you know, water and the Mickey Mouse ears and all that good stuff. So all of those different modes of vibration and modes of kinetic energy go into this internal energy of any substance. So the internal energy of a substance is a big deal. It's a state variable. It's something that if we really know it, then we know exactly what it depends on, that sort of thing. So if we actually have the equation of state for the internal energy of something, then we know a lot of stuff about it. Okay. Well, if you think about it, it should be common sense. And that's what the first law of thermodynamics is. If I add heat to the system, then that's going to have a potential to increase my internal energy. So I'm going to put a Q over here on this side, and I'm going to call this heat added. To the system, right? And that makes sense. If I say, let's take a balloon, I'm going to blow it up with some air, I'm going to tie it in a knot, and then I'm going to stick it in a big old vat of water, and then I'm going to start boiling that water. Okay, as that water temperature increases, what's going to happen is the molecules inside of the balloon are going to go faster and faster and faster. They're getting some of that heat delivered to them, and some of those molecules are in fact just going to cause their center of mass to be going faster and faster, in, out, left, right, up, down. But some of them might even have some of those molecules spinning about axes. All of that's going to go into the internal energy. Okay. Now, if instead of that, I said, okay, let's take, instead of a balloon filled with air, let's take a piston and a piston chamber. So something like you'd have in a car engine, which is basically a cylindrical, let's say, soup can for the simplicity of it. And actually, I did have one of my students build a engine out of a soup can, and that's a perfectly wonderful little engine he made. All you really need is to take the can lid, say, cut that off, and then I think he actually glued some leather around the side to keep the seal pretty good. He attached something on the back, maybe a screw to it or something like that, that had a rod like this. And basically what happened was he put a little sterno can under here, and that little sterno can would heat this up and cause that air to expand. Okay, so that's heat added to the system, right? But let's imagine now, because heat can be added to the system, I also unlock whatever's holding that piston. So for instance, I could have had a little weld right here holding the lid of the piston, and a weld right here holding the lid of the piston to a fixed volume. If I added heat, then not all of it's necessarily going to go to the internal energy. Some could go to the internal energy of the molecules and atoms in it, but some of it could actually go into work being done. Now, I might in fact think about that as this thing expanding is actually work being done on, by the system, in which case I would subtract that away from the heat added. And that's exactly the form of the first law of thermodynamics that we use here in physics. Okay. We say that the total internal energy is equal to the heat added minus the work done by the system on its surroundings. Okay. In chemistry, they usually use a plus, but in that case, they're talking about work done on the system instead of work done by the system. So that's the big difference here. So it's the same law that you did in chemistry. It's just we use a different sign because we were curious about heat engines and the amount of energy we get out. So for instance, example. Let's say 3,500 joules of heat were added to a cylinder of gas. I mean gas like air, not gas like gasoline. Okay. And the piston was pushed down further, compressing the gas and doing 2,000 joules of work how much? Whoa, I don't know what word that is. It went wrong from the get-go. Okay. So how much did the internal energy of the gas change? I'm gonna let you guys see if y'all can. I've introduced you to the first law of thermodynamics. That's all you really need to know. And I want you to all try to get an answer, and then I'm going to write down an answer, and we'll see which of you were actually able to figure it out, because that's part of the big thing about teaching is, you know, I want to be able to express something to you, and you want to have been able to listen so well that you can decipher what I say and put it into actual action. That's the same thing you want to be able to do with your textbook as well when you're reading it. So everybody try to work that out. I'm going to work out a solution outside of the screen, and then I'm going to bring it back up to you in a second. So Okay, hopefully I've all had plenty of time to think about this and work it out. Here's my solution. And this is the way I want you to think about it every time you do a first law of thermodynamics problem. First law of thermodynamics says that the change in internal energy of a system that you're looking at is equal to the heat added to the system minus the work done by the system. In this case, it blatantly said 3,500 joules of heat were added to a cylinder of gas. So heat was added to the gas. So Q is greater than 0, and Q in fact was 3,500. But here's the part where I tried to hide it a little bit. It says, and the piston was pushed down, further compressing the gas and doing 2,000 joules of work. Notice I didn't say what was doing 2,000 joules of work or anything like that. I needed you to understand that that meant work was being done on the gas. So work was being done on the gas because really what you see is a force applied downward, say, on this piston, causing the change in volume to go the same way. Okay, in other words, the force and the motion were parallel, so that was a positive amount of work done by the surroundings on the system. So the work done by the system would have been the negative of that, so that was negative 2,000 joules. So Q minus W became 3,500 minus negative 2,000, which is 5,500 joules. So you don't have to let me know whether or not you got that right, but I just want you making sure you guys are thinking correctly in terms of that, and that's the way it works. Okay. Now you will often see internal energy and the second law of the first law of thermodynamics written different ways. Let me show you a couple of those and explain what's going on there. The delta is probably the cleanest way to write it. The delta E is equal to Q minus W. That's probably the most clean and correct way of writing it. But sometimes you want to talk about small changes, so it seems really reasonable for you to talk about DE internal, and that's certainly fine. Here's the problem, though. There is, in principle, some function E internal that you could integrate and would be basically E final minus E of some variable final minus E of some variable initial, and you would actually get a value and it'd be independent of path. That's not true for Q or W. There's no such function as Q. There's no such function of W. Things can't contain Q. They can't contain W. They can only exchange Q with other things, and they can only do work on other things. So the way we keep you from making that error is we'll write d bar Q minus d bar W. Just to remind you, hey, you're not going to integrate this sucker. You're not going to integrate this and get some Q final minus Q initial. You're not going to integrate this and get some work final minus work initial. So that's another way you can write it. I just wanted to keep you abreast of that. And that's what they're talking about when they put the bar on it. It's not an exact differential. So if you've had differential equations or if you've had engineering thermo, you'll know exact differential equations are those equations where you've got some function times dx plus some other function times dy is equal to 0. And if you take the function, the derivative of the one in front of the x, but you take it with respect to y, and then you take the derivative of the one in front of y, but you take it with respect to x, and they're equal, then you know it's an exact differential. That's what we're talking about here. So if this happened to be one of those kind of differentials, then yeah, that would work. But these two are not that, so they're not going to be that. So that's really what that means. Now, there are different types of processes that can happen. For instance, an isothermal process. So I'm going to give you some vocabulary basically. So isothermal means delta T is equal to 0. Okay. Now for an ideal gas, that means this has to be 0. It's actually ideal monatomic. And that's because we've discovered early on that for an ideal gas, E internal equals 3/2 nRT. So okay, so that's why that's the case. That doesn't mean that's the case in general. That just means what is true for an ideal monatomic gas. Okay. Now that's one of the types of processes that can occur. Another type of process that can occur is one called adiabatic. And or adiabatis, as it's known in a country that I can't name right now because I'm making it up. So adiabatic, A-D-I-B-A-T-I-C. And what that means is delta Q slash Q is equal to 0. In other words, no heat added or lost. So that's an adiabatic process. Now that can happen by, for instance, in our calorimetry stuff that I showed you, you can make a really nice cooler so that you basically eliminate the vast majority of the heat getting in or getting out. That's one way of doing it. Another way of doing it is heat flows very, very slowly. Remember how heat flows? Basically, the object with the highest average kinetic energy molecules and atoms slowly allow those little molecules and atoms bang up against the object with the slower molecules and atoms, or with the lower kinetic energies, and slowly but surely that equilibrates to the thing with the lower average kinetic energy getting more average kinetic energy until it's exactly the same average kinetic energy as the other thing. So you can imagine that's a slow process. So if you're talking about for instance, a diesel or a gas-powered engine, that's probably going to be adiabatic because there's going to be a massive explosion. That explosion is going to push a piston down. There's almost no time for the heat to flow from the explosion of the gas cylinder into the walls of the cylinder. So that is essentially an adiabatic process. So that's another type of process. So the main thing is you're just thinking delta Q or Q equals 0. The next process is isoboric. I apologize for my dog being super helpful. So isobaric or isovolumetric are two different ones. You can probably guess which is which. Isobaric, you've heard of bars used as a measure of pressure. So if you had a pressure versus temperature plot like this, then isobaric would be this guy. And if you had this guy, then that would be a vertical line, and that would be isovolumetric, also called isochoric. Okay, so that's some other types of processes that can occur. Now, the big thing with that is, it turns out when you say work is equal to the integral of F dot dl, you can sort of say, well, wait a second, pressure is equal to force divided by area. So force should really be pressure times area, and you get the integral of pressure times area DL, ignoring the idea that they might actually not be perpendicular. In other words, that the pressure is not going to be perpendicular to the face, because that's the way gases and fluids behave. Then you all of a sudden have a new formula where A times DL is just surface area times length. That's a change in volume. So it's the integral of P dV. So you can see if you have an isovolumetric process, then work would be 0. So combining that and this, we say work equals 0. Whereas isobaric is nice because that just means the pressure is a constant. So work would just be P times delta V, where they're saying the pressure was a constant. So I can just pull that out in front of the integral and it's just going to be the change in volume. Ain't that nice? Ain't that helpful? Sorry, I'm using my impression of Ruthie from Ozark. All right, so the big deal with this, by the way, this work equals F dot DL, which turns out to be PdV. If you make a plot of pressure versus volume, as I did before, and you maybe consider a process that's, let's say, isocoric, followed by isoboric, followed by, let's say, isothermic. So that's a line of constant temperature. Then that process that went down this way, to the right this way, and up that way, the work done in that cycle is the area inside. Okay. In fact, they used to make machines for engineers when they would make for instance, a steam engine or something like that. The engineer could actually trace out the P versus V diagram, and it would automatically compute the area for them. Sort of like if you've ever seen one of those things that's sort of like an elongated clip, you squeeze like this and it propagates outward. I think it's not a pantomime, but something like that. Yeah, I'm sure y'all probably know the word now that I was giving you that part. But anyways, pantograph, maybe that's it, pantograph. It would reach out and grab something, and then you could pull it back in. Just like that, it was some kind of weird device. You'd roll over the curve, and it would just spit out basically a number saying the actual area, which is, you know, the work done. Therefore, it's something that's kind of useful to the engineer who's studying engines. Now, you can see what happens in the event that you had PdV and it was an ideal gas. Let me show you one example of that. Yeah, I still got plenty of time. So a couple of examples of that. We just saw one of them. If it was a isobaric process, that was easy peasy, right? But if we had work is equal to the integral of P dV, and we know that PV equals nRT, we could say, okay, well, work is equal to the integral of, solving for P, I'd get nRT over V dV. If you assume T equals a constant, in other words, isothermal, then you get nRT times the natural log of V final over V initial. So that's another result that could happen. If not, then you have to figure out some way to relate the temperature and the volume. But we already saw the other thing, which was for P equals a constant, we just get P times V final minus V initial. Okay. So those are just some common everyday results that I think are pretty trivial in terms of applying them. Now that we have that, you can look at the examples on your own. I want to go over the main material that I think sometimes stumps people a little bit. but there's a new formula we're going to use. It's the same formula we used before. We had used Q equals MC delta T, and that worked fine. But it turns out that something really, really amazing happens when we use a specific heat that's not in terms of mass, but rather is in terms of moles. So what we're going to do is we'll say Q is equal, instead of M, it's going to be equal to N times C times delta T. And we're going to use a capital C there. So I'm going to try to make that look even bigger so y'all would understand. But here's the problem. If I go and try heating a gas up at constant volume, then no work can be done. So all the heat's just going into changing the temperature. But if I go in by applying heat and just keeping a constant pressure on it, maybe by, let's say, doing something like this. We take a piston, we stick it on top of a cylinder of gas, okay, and we put a block that has a mass of 10 kilograms on it. Because of that 10 kilograms, that's a constant pressure. And if I add heat to that, I could add enough heat that it actually causes this to lift, so it could be some work done too. So in fact, there's not just one specific heat, there's a specific heat associated with constant volume, and then there's another one, which is a specific heat in terms of constant pressure. So that's our two new formulas. Now, you can probably figure this out. Hopefully you already have, but if you want to know what CV is, you're just going to take the molecular weight of the substance and multiply it by little CV. And if you want to know what CP is, you're just going to take the molecular weight and multiply it by little CP. Okay. In other words, look up on the periodic table, and that'll be the difference, because obviously if I take and divide, or if I try to solve this for CV, I'd get big CV over little m, over the m. That m divided into this m would give you the number of moles. So that's why that works out. Okay. So these are very helpful special formulas. And because of that, something really neat happens. It turns out you can play a little bit with the first law of thermodynamics, and we can say, okay, for instance, the first law of thermodynamics for constant volume. So let's say delta E, constant volume. So that's isochoric. Delta E is equal to just Q. Everybody recognizes why, right? If it's a constant volume, then there's no work that can be done. So delta E at constant volume is just Q at constant volume. Now, if you, again, deal with this first law of thermodynamics when it's not at constant volume, let's say it's at constant pressure, then you'd say, okay, at constant pressure, we'd get Q at constant pressure, but we'd also get, remember, it's minus the work done. So I would say minus P delta V. So I can now think of this as QP is equal to delta E internal with constant P plus P delta V. And I can think of this as QV is equal to delta E internal constant V. I should have put a V on that as well, right? But the change in internal energy is going to be the change in internal energy no matter what, whether you did it constant volume or constant temperature. You're basically just changing it. So if I did this, which is QP minus QV, so if I took QP minus QV, I would get, notice QP would be P delta V, and then delta E internal P minus delta E internal V. So that gives me 0. Well, that's nice, because if I look at an ideal gas law, PV equals nRT means that P delta V could equal nR delta T. So now I see QP minus QV is equal to P times nR delta T. Now I wanted, actually P delta V was nR delta T, so I don't even have to do that. I could have said, well, I'll do it like this. I'll put a P over here. That fixes it. So if I solve for delta V, for instance, that would be nRT over P. Now you see that QP minus QV is nR delta T, but we already said that QP, if you look up here, I should label this one P and I should label this one V. QP is nCP delta T. QV is nCV delta T. And that's all equal to nR delta T. Wow, we've got a big expression here. CP minus CV is just equal to R. So we just got a very generic result for any ideal gas. And if you actually look at the experimental data, which your book was kind enough to give us, remember, R is 8.314, but if you use it in the joule category, it's 1.99. So look at, for these various gases, if I talk about monatomics like helium and neon, CP minus CV experimentally is 1.99. And in fact, it's even 1.99 for N2, and it's 2.00 for O2. So even the diatomic's pretty close. And then when I look for triatomic, which would be like water and CO2, it's still pretty close, 2.03 and 2.00. So this result is a really sort of big deal, if you will. Not only that, it's such a big deal that we've defined another quantity called gamma, and that gamma is defined to be CP over CV. Reason why I'm doing this at all is just because there's this neat new thing, a neat way you can use the ideal gas law. So for instance, we know the ideal gas law says PV equals nRT. If you fix the sample of gas you have, in other words, you're not exchanging atoms and molecules at all, everything else stays the same, then you can obviously see that N and R is a constant, and you get PV over T is equal to a constant. That's in fact one of the ways that we can use the ideal gas law. In anything, as long as we're not allowing some gas to escape or to enter, then we know P1 V1 over T1 is equal to P2 V2 over T2. And as long as we use T in Kelvin, this will always work. And if the two volumes stay the same, you just got P over T and P over T. Or if the two pressures stayed the same, you got P over, or V over T and V over T. Or if the two temperatures stayed the same, you have P times V equals P times V. That's one of the ways we use the ideal gas law, and it saves us a lot of work. We don't have to actually put in the R and calculate the moles and all that. Well, if it's an adiabatic process, we get something even cooler. And I should go ahead and tell you this too. So if you continue this work on a bit further, you will find that CV, not only is CP minus CV equal to R, CV turns out to be, in fact, 3/2 R. And of course, 3/2 R, if I pulled that over to this side, that would be positive 3/2 plus 2/2, that's 5/2 R. So CP is 5/2 R. So those are two other results that your book gets for you. You can see it on page 512. But I just want to make sure you had those, because really all I'm shooting for in this last couple bits of minutes that I have is I want to show you that in the very special case of an adiabatic, quasi-static adiabatic ideal gas, so quasi-static adiabatic ideal gas. Well, I spelled gas with a Q for some reason. There turns out to be another thing like this that comes super handy, and that is pressure times volume to the gamma power. That's that same gamma that I showed you up there. That's equal to a constant. So just like I had P1 V1 over T1 equals P2 V2 over T2, I now can say P1 V1 gamma is equal to P2 V2 gamma. So that's a whole nother way we can work on ideal gas laws. Okay, again, quasi-static just means it's sort of a slow process. You wouldn't want you want it to be in equilibrium at every little state. So you're sort of moving it just a little bit, let it reach equilibrium, move it a little bit more, let it reach equilibrium, move it a little bit more, let it reach equilibrium. As long as you're doing that, you're not letting energy escape, then this equation holds. So that brings me to the last part of chapter 19, which is how heat is transferred. And we've got like 9 minutes for that. It's not a big deal. These equations are actually quite simple. And I'll relate them to everyday life as well, like I always try to do. So if you could imagine having a heat reservoir, and a heat reservoir basically is anything that is so big that it can lose some heat to whatever you're doing and still remain the same temperature, then that's a heat reservoir. Okay. So what I'm going to imagine is this is a heat reservoir. So for instance, the Earth is a heat reservoir. Pretty much a pool is a heat reservoir. Like if you get in a pool, it's going to immediately start stealing your heat, and its temperature is not going to go up very much at all, if at all, right? Because you're just a small amount of heat compared to what it needs to change its temperature. So in that sense, a pool would be a heat reservoir. A lake is a heat reservoir. So what I'm going to say is this is a heat reservoir, and it has a temperature. I'm going to call it T hot. And this is a surface area I'm going to call A. And it's in contact via, and I'm doing some weird perspective here on purpose, so we can see sort of both things. This is a cold heat reservoir, okay? And it has an area A as well, okay? And this has a length from here to here of L, and this will be T cold. So you can think of this as, say, this could be the insulation between the plywood on the outside of your house and the drywall on the inside of your house. That's what that rod could be there. Now, the plywood is in thermal contact with the environment outside, and on a hot summer's day, the plywood probably reaches fairly close to the same temperature as air temperature. And inside, the air conditioner has probably got the drywall to reach about equilibrium with the temperature of the room. Okay. Small changes in heat because of this piece of insulation is probably not going to help much. But what the transfer equation says is that the amount of heat, delta Q, crossing that length in the time delta T, remember this is time here, not temperature, that is directly proportional to the difference in temperature. And it's also directly proportional to A, right? If your hand's cold, you don't just put your fingertip against, something warm to warm up your hand. You put your whole hand against it because your whole hand is cold and you want that whole area to get heated. Or similarly, if you have a burner on your stove that big and you have a burner on your stove that big and you got a pot that big, you don't put that big pot of water on that little burner. You put it on that one because it's about the same area. So it makes sense. The larger the area, the larger the amount of heat flows per time. Of course, you'd also expect the longer this distance is, the slower it's going to travel. And that's also true. So we're going to say this is T hot minus T cold, because heat always flows from the hot object to the cold object. And this right here would be called a temperature gradient because it's literally a change in something divided by distance. Now, the big thing here is, how does this change if this material is, say, aluminum or fiberglass? Well, it changes by a constant K. And that constant K is called the thermal conductivity. Everyday life, nobody uses this except us physicists, scientists, and stuff like that. In the real world of, let's say, construction, what they use is L over K. So they take this L and this K, and they divide the L by the K, and that is an R value. So for instance, you can get R13 for your 2x4 walls or R19 for your 2x6 walls. And the reason the 19 is bigger than the 13 is because it's made for 4.5-inch thick walls. Whereas the, 5.5-inch, whereas the R13 is made for about 3.5-inch thick walls. And if you try forcing the R19 into the 2x4 walls, you're actually going to get a value that's less than 13. And 13 is the bare minimum. So that's one equation. And that's how heat is transferred through conduction. So that was conduction. And the other equation is through radiation. There's also an equation via something different called convection, but we're going to ignore that. Really, what we get for radiation is delta Q over delta T is equal to something called the emissivity, which really tells how reflective it is versus how much it can absorb, times sigma, which is a constant we've determined experimentally, times the surface area, A, times, and this is the kicker, T to the 4th power. So let me write out what that sigma is. Sigma is 5.67 times 10 to the -8, and that's watts per square meter per Kelvin to the 4th. Okay. Now this is really like, this is your wattage. This is like the 100 watt on a 100 watt light bulb. Or if you want to talk about the total amount of radiation put out by our sun, that's this quantity right here. If you want to talk about how much it puts out per unit area, you divide both sides by this area here, and that would go over there. And that's something called the flux. But what this tells you is that, hey, if I have a sun that has a temperature of, say, 10,000 Kelvin, And then I have a similarly sized sun. In other words, the surface area is the same, only instead of 10,000 Kelvin, it's 20,000 Kelvin. Then the sun that's 20,000 Kelvin will put out 2 times 2, that's 4, times 2, that's 8, times 2 again, that's 16. It'll put out 16 times as much energy per second, or as much watts. Okay. And everything that has a temperature greater than 0 Kelvin is putting off this heat, period. So if you're in a room, you're putting off this much heat based on your body temperature and your surface area and your emissivity, which we sometimes just pretend is 1 because that's what a black body would be. But at the same time, the atmosphere in that room that you're in is applying the same amount of heat to you, only with a temperature associated with the temperature of the room. So you're constantly absorbing energy from the room, given by sigma, or excuse me, the emissivity times sigma times your surface area times the temperature of the room to the 4th. And then you're putting out your emissivity, sigma, your surface area times your body temperature to the 4th power. And in fact, if you do that calculation for a 70-degree room, you'll find out that each human puts out about 100 watts. So those are the 2 equations that I wanted to introduce you to. You now have everything you need to know to do these problems that are handled in this particular part of the chapter are really, really trivial. So I don't just go back to you having a problem. Time's up. You guys are free to go. We have now finished chapter 19. The practice test is up for these chapters. I'll wait for the last person to leave, and then I will go. Have a good day. Thanks for coming.
Have a good day, Professor.
You too. Sean or James, do you have any questions? Type them if you got them. All right, I'm going to assume you are not there. Have a good day.